Hello dear students, I hope you're doing great. This is a video guide to the solutions of the R Radiant exam practical 2 based on the dataset Titanic. You can find the dataset and the handle with the questions and the solution on Blackboard. So don't forget that in the exam you will have 45 minutes to solve 16 and not 15 questions. I'm sorry for this bad news. As you know, I'm overwhelmed with my workload, so unfortunately I have very little time to prepare this video. There is close to no editing, it's quite slow, a lot of waiting times, so sorry about that, but I hope that nonetheless you will find it useful. So please provide some feedback, and if you really think that it's useful, I might try and do another one for the next topic, which is simple linear regressions. Enjoy! Before starting the exam, you will be provided with a password to log in our secure network, and also with a link that you can use to find the R test on Blackboard. This is a test I prepared for another class. Your test will have more like the same format. In particular, the test information will present the dataset with detailed descriptions for each variable, and also a link to the dataset will be available. I suggest you download the dataset on your desktop, and then that you open two RStudio interfaces. From one of the interfaces you can launch Radiant with the usual command radiant, and then you will only be working with three windows: the one of the quiz, the one for Radiant, and the last one will be an RStudio window if you prefer to run some commands on RStudio. Great, so the first thing is to load our dataset from the desktop. My first suggestion is, of course, to have a look at the dataset. Here we're working with data Titanic.R data, which contains a list of passengers from the Titanic, the class, whether they have survived or not, the disaster, gender, age, and so on. From the tab view, you can see the full list. Let's start answering these questions. Which percentage of people survived the disaster? Many times when we are using categorical data, the pivot tab is very useful. So in this case, we can specify one or more categories, but one will be fine. And we create a pivot table which categorizes the individuals based on our categorical variables. So, as you well know, we can normalize by the total using this command here, and then recreate the table to see that 40.7% of the people survived the disaster. Be aware of the decimals required in each question. So, for example, here, if I'm providing a percentage and I'm asked for 3 decimals, then I will need to add 2 decimals with this option here, so that I can report 40.748. Second question, compute the average fare of people in second class. When we have to compute means, standard deviations, coefficients of variations, and so on, we use the tab Explore. So we want the mean, which is already here. I want the functions to apply. But we want only the mean of people in second class, and in particular of the fare they paid. So the numerical variable is fare, but I want to group the individuals by class so that I can get the mean for each of the classes. In particular, the average fare of people in second class is 21.855. Question number 3. The age distribution of which class presents the highest interquartile range? The first thing I can think of is just to look at the box plot, right? From the tab Visualize, distribution stem for histograms, so I want to look at box plots instead, and I want the box plot of the age in this case, and one box plot for each class. So let's see what it looks like. Great, it is trivial. The interquartile range, which is the difference between the third and first quartile, seems to be significantly higher for the first class. Okay, it is represented by the body of the box plot. However, if you want to double check and be even more precise, we can go back to the Explore tab and compute for the variable age divided by grouped by the class. Well, we can compute the 25 and 75 percentiles. Let's see what it happens. Great. So the interquartile range is given by the 75 percentile minus the 25 percentile. So for example, for the first class, this is around 50 minus 28, so we have an interquartile range of around 22. 36 minus 22, here we have around 14, and here we have around 13. So definitely the highest interquartile range is for the first class. This question is done. Report the survival rate of people who embarked from Childbirth. Not sure how this is pronounced. So again, two categorical variables. So PIVO is the answer, survivals, and embarked is the other categorical variable that we can use. So we have to report the survival rate of people who embark from childbirth. So we here, in this case, the pivot table is normalized by the total, but we want to normalize by row instead. So I can see that out of all people in from this place, right? Well, quite a high percentage have survived. So the rate, in this case, that I'm asked for, will be 0.623 up to the third digit. Question number 5. Within the group passengers with at least 2 parents and children, what is the percentage of survivors? Okay, this is a bit tricky. We don't need the embarked factor anymore. We only look at survived variable. So we did this before, normalizing by total, and we got the percentage of people who survived. But now I want the percentage of survived only of the people with at least 2 parents or children. How we do this by filtering the data. In particular, the data set. We need to filter the data set so that the variable pH, which is basically the number of parents or children. Okay, we want to filter the data set so that this variable is at least 2. Okay, so these the pivot will now be recalculated using the filter data set, and the answer is in this filter data set. The percentage of survivors is 42.542%. Don't forget to untick the filter if you're asked for similar questions. Otherwise, you're doing all the calculations for the filter dataset and not the full dataset. Question number 6. If the survival probability of a passenger was 40%, what would have been the probability that at least 400 passengers have survived? So, we can do this in 2 equivalent ways, or maybe more, but these are the ones I could think of. Let's go to our studio. So we have in total a number of passengers of, we can see it here by not normalizing. So there are in total 1,043 passengers. So 1,043 passengers. Okay. So, and we are assuming that the probability of a passenger to survive was 40%. And this is a bit like our null hypothesis, that the survival rate is 40%, even if we don't really know it. So we can approximate the number of survivors. So it is a binomial distribution, but it can be approximated by a normal distribution. So to calculate the probability for at least 400 passengers to survive, what I'm asked for basically is for the probability for a normal distribution to be higher than 400. Okay, so higher, you know that when we look at the upper tail, we use lower tail equal forms, and this distribution, this normal distribution, has mean equal to 0.4, so P0, the probability of a passenger to survive, times the total number of passengers. We also have to specify the standard deviation, and in this case, the standard deviation of a single Bernoulli, which is then multiplied by square root of n, is given by square root of P0 times 1 minus P0 times n, and the square root of all of this. The probability for our my normal with mean 0.4 times the number of passengers and the corresponding standard deviation is, this should go away. So I'm asked for the percentage, so 86.151%. Alternatively, the probability for at least 400 passengers to survive can be seen as a sample proportion, right? So I have that the sample proportion of survivals is 400 divided by the total number of passengers, and P0 is the mean, and the standard deviation will be very similar to what we have written before. I'm copying the upper tail as well, but instead of times n, is divided by n. Okay. Great, so this is done. 7. If the survival probability of a passenger was 40%, what would have been the third quartile of the distribution of number of survivals? Great, so we have the distribution of already determined before. So what is the third quartile of a normal with this mean, this standard deviation? So we forget the lower tail. Well, to compute the quantile instead of the probability, I will use the function q norm, and I want the third quartile, so this corresponds to the 75th percentile, and the answer is 427.8714. Let's do this example in radiant as well. So we need the mean of the distribution we want the quantile of. So for example, in this case is 417.2. So we move to radiant, go to basic, probability calculator. I want the probability. I can specify the quantile of a normal distribution this way, so specifying no lower bound and the upper bound of 0.75. Okay, here. However, this is for a standard normal, whereas like my normal has this mean 417.2, and the standard deviation is given by 15.8215. Okay, no problem. So the answer is 427.871. So the probability for my normal to be lower than this is 0.75. Therefore, 427 is the third quartile. And it's the same as the calculations in R, clearly. Great, almost halfway through. Report a 99% confidence interval for the probability of survival in such a disaster. Okay, so we can do this by estimating a single proportion. So in particular, we want to estimate the proportion of survivors. Choose the level, so we are either estimating the level of the probability of survivors or not survivors, but we want to estimate the probability of survivors in this case. And this is it, really. So we want our confidence interval to be symmetric around the point estimate. So the point estimate in this case, so the people who survived, was 40.7%. This is what we calculated in question 1. And the confidence interval, two-sided, okay, so centered around the point estimate, is between 37.7% and 43.8%. Okay, let's move on. Report the p-value. Question number 9. Report the p-value of the test with null hypothesis that the average fare paid by passengers who survived is the same as the average fare of passengers who did not survive, against the alternative hypothesis that the average fare, okay, of passengers who survived is higher. Okay, I think it's clear. We have to compare two averages, so this is the suitable tab. And we want to divide the two groups according to whether they survived or not. And we want to test the averages of the fare. Okay, you can play around with the alternative hypothesis and then double check that these alternative and null hypotheses are the one you want. In particular, in this case, the alternative hypothesis is that the average fare of passengers who survived is higher. So this is a one-side hypothesis, and this is the correct option that we want, right? The null hypothesis is that the two averages are the same, and the alternative is that those who survived actually, on average, paid a higher fare, and the p-value is 0.001 for this test. So apparently we reject that the mean, the average of the two of these two populations are the same. Question number 10. Report the p-value of the test with null hypothesis that the average age of passengers who survived is the same as the average age of passengers who did not survive, against the two-tailed alternative. Again, we are comparing averages again between the groups of survived people and those who didn't make it. But we want to estimate the averages of the ages. So apparently those who did survive were on average 28. Those who did not survive were on average 30. However, this difference, if we consider the two-sided, two-tailed alternative, so two-sided, okay, the p-value for this test is 0.068. So at the usual confidence level of 95%, that corresponds to a significance of 5%, we wouldn't reject the null hypothesis that these two groups had the same average age. Question number 11. Report the percentage of women out of all female passengers and men out of all male passengers who survived. This is something that we can again do using the pivot table. So survived is already there, but now we want the gender, sex. Great. So I want the percentage of women against all female passengers. So I will normalize by row. Great. So 75.130% of women survived, whereas only 20.548 men survived within the female and male sample groups, respectively. Question number 12. Is there an association between the variable class and survival? we are still here. So instead of sex, we will compare the different percentage of survived and not survived divided by class. Great. So I think it's more reasonable to normalize by row. Like it seems obvious that we have a very different, depending on the class, we have a very different percentage of survivors or not. So definitely there is an association, and in particular for the first class we have a survival percentage of 63.475%, whereas like for the third class it's only 26.200%. You know that you can see a plot of what's happening. Like in the first partial, you also should know that, okay, the most suitable plot in this case is a stack plot, but probably not this one. So we have to rearrange the categorical variables and recalculate. This is the stacked bar plot that we want, right? So depending on the class, we really have a different distribution of survived and not survived. Okay, we're getting there. Calculate the correlation between the variables age and fair. This is easy. On the basic, there's a correlation tab which allows us to choose a subset of variables. They can be numerical, they can be dummy variable, they can't be categorical variable, I believe, yes. So we have only a factor here, survive, because it's a 0, 1, and we calculate, and this calculates the correlation coefficient for us. So between age and fair, there's a slightly positive correlation, which is 0.18. What's the name, 14, of the oldest passenger? Did they survive? This is a simple question. If you go to the View tab, we can arrange the passengers according to age. Barkworth is the name of the oldest passenger, and Mr. Barkworth did survive. Okay, great news. Last question, question number 15. Report the p-value of a suitable test for the null hypothesis that the passengers in similar cruises are divided between first, second, and third class according to the proportion. 25%, 25%, and 50% respectively. Okay, this is a chi-square test to compare our sample distribution with respect to our known distribution, and this can be done using basics, goodness of fit. So first we need to choose the category. So in this case, the categorical variable will be P class. Okay. My suggestion is to tick at least the observed and expected boxes. So you can see that under each category we have, like for example in the first one, we have 282 individuals in first class, 261 passengers in second class, and 500 in third class. If if the passengers were equally distributed among the three classes, we would have 347.67 passengers per class. But this is not our null hypothesis. Our null hypothesis is that in the first class there are 25% of the passengers. In the second class we have 25% of the passengers, and the remaining half, it's all in third class, sorry. Enter. Okay, so if these were the true probabilities of belonging to a specific class, we would see 260 passengers in first class, same in second class, and double as much in third class. This is slightly different from what observed, but not enough apparently. So the chi-squared test has the null hypothesis that this sample comes exactly from this distribution. Although it's not the same, the observed value are not exactly as we expected, they're not very different either. So the p-value for this test is 0.270. This is the number we have to report here. So the exam is done. Don't forget to report all of your questions. Don't forget to click the button submit at the end of your exam. Don't leave the room without submitting. And this is it. Well done.